Good afternoon, all. I will now request our guest of honor, Professor Divyendu Nandi sir, to start with his lecture on our astrophysical ecosystem, how the stars govern planetary habitability. Sir, over to you.
अच्छा so the Bluetooth thing now that you can do it automatically, right? Right? This one I think is better to switch it off. So, okay, good afternoon. It's a great pleasure, also honor to be invited to this very traditional, prestigious organization, and particularly by the Geological Institute, which I figured out is the oldest such organization in the country, and the Geology Department of Presidency University as well, which is one of the oldest departments in the country. If you have not seen, and some of you are astronomers have not, I don't know, only seen the old lecture theatre. Beautiful place. I made all of them stand there and take a picture of it. It's made up so beautifully. You may lack for money, but it's certainly don't lack for tradition. And it's really a great honor to be part of your AGM today. So I want to talk about our astrophysical ecosystem. The more you grow old, and do your research, you realize that when you're young, you are very ambitious and you only worry about the science that you do inside us. And you think that the science that you do is the best, and everything else that everybody else is doing is not really up to the mark. When you grow old, that changes, and you slowly realize that everything else that you have shone aside will also someday come back and play a role in your lives and in your research. And this is certainly true for my research, and many of us um, who work with the sun particularly. We used to see the sun in isolation as a star, but I think in the last few decades or so, we have realized that the sun has very important consequences for not just our space environment, um, also planetary planets. And the solar system provides us with a beautiful opportunity to document those interactions and allows us to take the understanding to search for habitable life elsewhere in the universe. This is the field of exoplanets and exoplanetary habitability, which is really driving the growth of astrophysics pretty much everywhere else in the world except India. We are followers, so we will wake up to the 20 years down the line. But I hope that the Presidency University, which has now a new center for astrophysics and has this very old traditional uh, geophysics department, will work together and will hire some exoplanetary scientists. We'll bridge the gap between what you folks do and what they do, and try to do something truly disciplinary which is happening in the world across it. I hope you can keep that in mind. All right. So with that, I will begin my lecture. My lecture is not going very technical. I mean, I talked to some of your students and I realized that this is going to be a diverse audience. So I will speak about our research, about our field, but I will talk about the interconnected themes, and it will be more of a story that I hope will leave you with the impression that I want to leave you, which is that our life is not in isolation from the cosmos, that our life is very much dependent on the intertechnical process that goes on inside of stars. Not just the sun, but very far away in the universe and newer existence to such astrophysical processes, and therefore I like to call it the astrophysical process. Let me begin this story with the Voyager 1 mission, which is the furthest human-made object that has traveled in space. Right now, it is 24 billion kilometers. What you see here is the solar system. The solar system is encompassed in this rings of the sun, the plasma rings. It defines the heliosphere. the sphere of influence of the sun. So the plasma wind of the sun meets the interstellar boundary and interstellar medium, which exists beyond the heliosphere. And you have this sort of shock wave of the solar system and the heliosphere moving to the interstellar medium. It's kind of a cocoon within which the planetary systems exist. The Voyager 1 spacecraft has in fact traveled outside the solar system and has exited the boundary of the heliosphere now. It is the furthest man-made object from Earth. It carries this known as the golden disk, which has the encyclopedia of knowledge that humans have discovered or created. It carries sound waves of music, sounds of the seas. It carries ragas and classical music by various composers. In fact, it carries the raga Bhairavi, a song called Jaat Kaha Ho, Where Do You Go, by Kishore Bhai Ketar. When this was about to exit the solar system, legendary astrophysicist and science popularizer, whom all of you heard about, possibly, at least the previous generation, Carl Sagan. He convinced NASA to turn around the cameras of Voyager 1 and take one last picture of planet Earth. That picture is here. You don't really see it very well, I think, in this hall with all the lights. The streaks of light that you see actually sound this is aberrations in the instrument. But if you notice that little white dot there is the Earth. So this is one of the furthest pictures of Earth ever taken by human-made mission, and this picture became iconic and was named the Pale Dot by Carl Sagan. And this picture epitomizes the reality of our existence in the context of the universe. It's also a motivation for me today to speak about how we are connected to the universe and how our life is connected to the universe. Before we talk about life, let's begin with that. So what you see here is the constellation of Cassiopeia, which is a collection of stars. Constellations are usually a collection of stars and galaxies. So Cassiopeia is a very old collection of stars, in the sense that if you look at this, you usually see stars which are very rich, and many stars are very old stars, which have pretty much lived through their life, whereas newly birth stars are much more active and much more brighter, and they're more bluish. It's like the Meridian spectrum, the hotter stars are more bluish, whereas the colder ones are in the red spectrum. So this is where most of the stars are old and they're actually about to die. And very massive old stars die spectacular deaths. They die in this process known as supernova explosions. And what we see here again is actual observation in false color, but an actual observation of a supernova explosion in a system known as Cassiopeia A, which is in the Cassiopeia system, which is an old massive star which is essentially collapsed and finished its lifetime. When this happens, the collapse of the star releases gravitational energy, which blows out the outer shell of the dying star in a shockwave. And that shockwave travels distances which are humongous. They travel to intergalactic scales, and they carry the material from that dying star and distribute it toward the cosmos. If you don't believe that material can travel so far, please believe me, because in each of those explosions, the energy that is released is 10 to the power 44 joules. That's the equivalent of 10 to the power 32 atomic explosions happening at the same point in time. So when a supernova happens, the amount of energy the supernova releases is the amount of energy that the sun will ever release in its whole life. That is the amount of energy that's then important to the kinetic energy of the shock waves, which carries the material of the dying star out into the universe. And in this death is the seeds of life. And I will come back to that. We'll talk really the collection meandering of various stories intertwined together. I'll come back to that. Why is it so important? Okay, so this is how massive stars die, and they actually seed life, but that story I'll come back and tell you. Before that, let's go back to the beginning, about 13.8 billion years back to the Big Bang. I'll be very brief about it. I will not go into technical details, but we believe that the universe was born in again a massive explosion, which is known as the Big Bang, from a singularity, which where most of the energy of the universe was contained. Early on in a phase was the inflationary phase, it expanded rapidly, and when it was expanding, it cooled. During the cooling, the fundamental particles produced during the Big Bang started coalescing together to form electrons and protons. And subsequently, about 300,000 years after the Big Bang, the electrons and protons, which constitute the primordial plasma, started combining together to start forming neutral atoms. When you start forming neutral atoms, the photons, the radiation that exists in the universe, they decouple from the matter. Before that radiation and matter was coupled, the universe was opaque. So at this point in time, about 300,000 years into the life of the universe, because the radiation decoupled from the matter, photons could travel free. So the earliest that we can actually see back into the universe is really about 300,000 years back after the birth of the universe. That's the cosmic microwave radiation that comes from that phase. And then about it still started went on expanding. At about 1 billion years into the lifetime of the universe, the first structures in front of stars started forming. About 10 billion years in the lifetime of the universe, the first stars that were born finished their lives and they started dying. And then many of the deaths would imply to either end up as a white dwarf or a neutron star, in a supernova explosion or a black hole. So that happened around 10 billion years into the lifetime of the universe. So this is the time when the material inside of stars that was cooked up was redistributed in the universe through the supernova explosions. That's about 10 billion years in the lifetime of the universe. And now we are about 30.8 billion years old as the universe. So if you think of when could life have initiated, we believe that it could not have happened before 10 billion years of life in the universe, because that is when the mixing of materials essential for life started happening. And I will spend a little bit of time explaining that. So, how to form structure or matter in the universe? I know that not everybody here is a physicist, but it's good to kind of brush up on the basics, these are the basic physics here. So, hydrogen atom is the simplest to form, and of course, helium also is the next simplest atom. So, much of that is actually formed in the primary and nucleosynthesis of these elements. So, the hydrogen atom is easy to put together, just a proton with electron together, that's easy, right? But light charge is different, and unlike charges like that. So when you go to higher mass elements, going from hydrogen to helium to higher mass elements is actually a different process. Because in the nucleus of a helium atom, you have two neutrons and two protons. So you have a proton, when you put together another proton, and the two protons are both positively charged, and they try to repel each other, right? And that's a problem. And the more higher mass elements you have, which means the more protons you have in the nucleus, it gets more and more difficult to put together more and more protons to build higher mass elements, which means that you now need much higher energies to build up high mass elements. This is kind of encapsulated here. So if you have a fixed proton in the center of the atom, and you want to put in another proton there to build a higher mass element, you have to overcome what is known as the potential gradient, Coulomb gradient, the Coulomb repulsion between the charges, right? So that's the potential gradient. You can overcome that if you have enough kinetic energy. The approaching particle, approaching proton has enough kinetic energy, which implies that this kind of reactions are possible if you generate a system where there is high temperature, which imparts a high kinetic energy to the approaching particle. So, for example, when you are doing nuclear explosions, you usually have a sort of a seed detonation, which starts the main nuclear reactions. It actually needs a seed detonation. This is something that is easy for stars to do because the interior stars have extremely high pressure. So you're actually squeezing into the matter. Protons are existing with neutrons and electrons in a highly dense state. Temperatures are very high, so the particles have high thermal energy, implying that they have high kinetic energy as well. So they can overcome this potential. That's the classical picture. Actually, you also need the phenomenon of quantum tunneling to be able to tunnel through the potential barrier. And this is sort of something that we often ignore, that classically it's actually not often possible to have nuclear reactions. You need to have this probabilistic phenomenon of quantum tunneling to be able to put together higher mass elements. So this is what happens really in the nuclear of stars, where the stars are cooking pots. This kind of in the natural world, in the Earth, it doesn't happen. So once you realize these elements cannot be formed, okay, these are formed somewhere far away in the interior of stars through this process called stellar nucleosynthesis. You can build up higher and higher mass elements, not up to it stops at iron because of the iron binding energy is extremely strong. But these typical set of reactions that you see, for example, in the sun, where you start off with hydrogen and helium, and you can keep up building higher mass elements to beryllium, lithium, carbon, oxygen. So through this set of reactions, and it involves two chains of PP1 and two chains, you eventually build up what are the building blocks of life. Carbon is required to form cellular matter. Oxygen is required for life as we know it. Nitrogen is also required. Um, However, you don't create very massive elements in stars, even the very massive stars where it stops at iron. For that, you need to go to supernova explosion. Because I was saying that the death of stars actually see life on planets. The reason being that in the interior of stars, you can have temperatures on the order of 20 million degrees Kelvin. But in the shockwave of supernova explosions, when it happens, you can have temperatures which can be on the order of a trillion degrees. So that's 1,000 billion degrees. And in those kind of temperatures, the neutrons are imbibed with enormous energies that they can really rupture through atoms, which are high mass elements. And for example, this set of reactions, when you first have, let's say, an element with atomic number Z and atomic mass A, and you combine that with a neutron, you have a higher mass element, but the charge given is the same, is typically unstable. So that through a beta decay, it gives us a electron, and then the charge increases. And now you have a stable element. So starting from AXZ, you can get to A plus 1, and a new element Z plus 1. So you essentially, this almost brute force energies that's there, you can start producing higher and higher mass elements. Therefore, elements, for example, iron, which cannot be produced in the nuclear stars, is actually produced in supernova explosions. If I take up the iodine that exists within our thyroid glands, we will not live. It's important to realize this, that we are made up of elements that has not only been cooked up in the nuclear stars, we are made up of elements which have been cooked up in supernova explosions, which are the death throes of the very massive stars. And by virtue of the fact that these humongous explosions mix these elements up that have been produced throughout the universe, then they found their way into various planetary systems like Earth, that we have the basic building blocks of life. This is a period table as you don't know. Most people don't know. Certainly not jealous. Most of it is sorry about that, but this is this is where most of the elements are produced. They are mostly produced in the nuclear stars, in the primordial nucleosynthesis, and many within dying stars, which are the supernova explosions. Some very few elements can be produced through artificial means on Earth, but most of the period as we know it, comes from the cosmos. This is something that is very important for us to keep in mind, that the cosmic cooking pots produce the elements that make us up, that make up the world. Fine, so we form atoms, we form elements, but how do we form structure? Okay, so we see structures, we see Earth, we see stars, we see galaxies. How do we form structures in the universe? Well, that's easy. That's easy because we know that gravity is attract two masses. So if we have matter, then attract each other. Fine. So if you have a uniformly distributed gas in the universe, that's sort of expected in interstellar medium or in the primordial setup. If you have some instability where you enhance the density or the material in particular part, it will attract significantly the material around it and start clumping material together and forming life. So the natural question that arises, is that why is the whole universe not one big whole cloud of material? Why do we have a stable star? Why is it not keeping on collapsing and getting into another similar? Right? So we see stable planets, we see stable stars. So what's going on? Right? Okay, so the gravity attracts, but there is a competing force, which is pressure. So as soon as you start pulling material together and clumping them together, the pressure of the gas is rising. The temperature, if you look at the ideal gas law, pressure rises, the temperature rises. The temperature keeps on rising, more and more matter is being activated into a region where gravitational stability happens, creating what is known as the protostar. It's like the, the mother of a star before a star is born, which is much more material than a star typically. So that's contracting. While it's contracting, the temperature and the pressure in the inside is tremendously increasing, finally triggering off nuclear reactions. When the temperature and pressure can trigger off the nuclear reaction, suddenly you have a source of thermal energy in the interior, which then drives the outward flux of protons and thermal energy, thereby creating a pressure gradient, which is essentially trying to now balance the inward pull of gravity. So the force due to the outward pressure gradient balances the inward pull of gravity. And eventually, at the very fundamental level, is this balance between gravitational attraction, gravitational forces, and the outward forces due to pressure gradient in a star which is having nuclear reactions in the center is what holds a star together and makes it stable and doesn't allow it to contract from until you lose the source of energy, which is the nuclear fuel, the hydrogen or whatever we're converting to higher mass elements and there's a mass loss. And once that nuclear fuel is lost, then a whole series of evolutionary steps comes in place, and the star essentially collapses and sort of dies and ends up either being a white dwarf or a neutron star or a black hole, depending on what initial mass it was born with. But typically, in the main sequence, the youth and the main phase of a star like the sun, it's in balance. So the pressure forces and the gravitational forces are balanced it, primarily because the existence of nuclear fuel, which is keeping the star stable against further collapse due to the outward gradient of pressure. Um, you see an example of such a system when new stars are being born from interstellar media in the large imaginary cloud. This is observation by the Hubble Space Telescope. This brown gas that you see is the interstellar media, which is a diffuse distribution of gases. Gravitational collapse in this interstellar media, this diffuse gas producing stars in the interstellar media, and the very bright sort of bluish white stars that you see are the newly birth stars, whereas the reddish stars are the slightly older stars in the system. So this is like a stellar nursery where you see star formation taking place. So the sun and the planetary system was born to such a process, through a protostar which collapsed due to gravitational instability. And a disk formed around the central region, which further collapsed to form a sun. And from the disk, instability started forming different planets. And so essentially, we have then the solar system of different planets around the central star, which was all birthed from the collapse of a larger distribution of gas, which is known as the protostar. So stars are extremely active um, um, systems, unlike well, I know you're not going to like this, but unlike planets. So, in the sense that in planets, of course, it's very active. You have processes that is happening a lot on the surface, geological processes, mixing. You also have in planets which have a liquid core. You also have convection. All of this is hyperactive inside a star because in the core of a star you have nuclear fusion going on. So the energy is being generated there, and then you have this region known as the radiation zone, where the energy is transported by radiation. And then the photons hit a region which is opaque to radiation, and that's known as the convection zone. So the passage of radiation is stopped. So the photons, the energy in the photons essentially are deposited in the plasma, which is the base of the convection zone, to heat up the plasma. So now gravity is pointed downwards. If you have a material which heat up and it expands and becomes lighter, then ultimately this principle tells you that it's going to rise up against ground. So it rises up in the outer parts, which is the surface, then it starts radiating energy. And that is why it starts shining. You have this radiating energy, the conductive energy, and then finally, whatever reaches the surface is radiating away. It cools because of the radiation, becomes dense and again sinks. And you see this convective glow in the outer part of the sun, which is essentially known as the convection zone. So the luminosity of the sun is something like 3.84 10 to 26 watts joules per second. That's the amount of energy that this processes are transmitting. And that's why we call it hyperactive. And that's also a very good constraint on what's energy, that's how much nuclear energy you can produce in the sun. Because eventually what's produced for a stable star has to be able to escape. Otherwise you have a stable system, right? There are multiple other processes like large scale flows of plasma, called diagonal circulation, much like the Hadley in the atmosphere of planets. And remember that everywhere inside the star, you have material existing which is mostly above a few million degrees Kelvin. Near the surface, it finally comes down to something like 6,000 degrees Kelvin. So matter exists in the ionized state. So it's broken up into ions and electrons. And then you have these large scale motions, which implies that you have large scale currents in the system. And from Maxwell's equations, it follows that you can now start producing electrons. So in fact, stars are giant planets, and the process is not very dissimilar to what happens in the Earth's outer. So you have the liquid outer core of the star. There also convection happens, but the convection is not happening in the Earth's core, in Earth's outer core because of the reasons that's happening inside the sun. It's just that convection is happening to a temperature gradient because the Earth is cooling from the surface, right? So that temperature gradient is varying convection, right? So the Earth also has a mechanism just like the sun, because iron, liquid iron is conductive, that you can actually start producing magnetic fields, and this is one of the macro-dynamic dynamo process. The sun, in fact, through this activity in the convection zone, it produces very strong magnetic fields, which is responsible for much of its hyperactivity, as we have come to know in the last 40 years or so. So there is regions known as spots. And it turns out that all stars, mostly active stars, have spots. And these are known as star spots. For the sun, they're known as sunspots. The first observations of spots was actually done by Galileo Galilei, Mr. Scheiner, and um, Johannes Fabricius in the 1600s. A very interesting story here. Christoph Scheiner was a Jesuit priest. Um, he and Galileo simultaneously observed spots on the sun. But the Bible said that the stars are, and all heavenly bodies are perfect in start of blemishes. So Christoph Scheiner, who was the Vatican observer, essentially concluded that these spots must be dark clouds floating above the surface of the sun, or in between the sun and they cannot be blemishes on the sun because the sun is a perfect body. Because his interpretation was clouded by what he had, what was the current um, doctrine. Galileo, on the other hand, of course, based on his observation, particularly the fact that they seem to move to a negation, um, uh, apparently coupled to the surface rotation of the sun, concluded correctly that these are actually spots on the sun. And that and many of his other discoveries and his interpretations which went against the current doctrine landed him in trouble. And many of you know that he died in imprisonment, almost died by the time he died. Okay, anyway, so this spots, this is a painting by Galileo, right? This is the actual painting by Galileo as he saw sunspots, 316 So, you see them through much better high resolution telescopes that we have now. And you see not only these nice structures in sunspots, you also see the convection patterns, the convective granules on the surface of the sun. And you see the size of the sunspots. This is actually comparable or usually much bigger than the size of the Earth. So you can fit in a couple of Earth inside the sunspots. In about early 1900s, with the discovery of instrument as a magnetograph, it was discovered that the sunspots are strongly magnetic. That is the first time we came to know the sun or stars have strong magnetic fields, not stronger than the Earth. Now, of course, we know that there are stars like pulsars, magnetars, neutron stars, which are much stronger, even than the sun, right? So typically, the magnetic field inside of the sunspots is on the order of something like 4,000 Gauss. It could reach up to as high as 10,000 Gauss. So some of the strongest magnets certainly in the solar system. Um, so these magnetic fields from inside the star is produced because of this vigorous convection escapes out from within sunspots and they permeate the outer atmosphere of the sun. Um, Most of you are geologists, so you would know that right here, right now, my fingers are touching magnetic fields. Right? Can you see? Right? That's the Earth's magnetic. Sun, on the other hand, you can actually see the magnetic fields. Through a set of beautiful positions, we don't have the time to explain why. But it's just that what happens in the outer atmosphere of the sun is a million degrees hot. And that's known as the outstanding challenge in astrophysics, the coronal heating problem, in which we found the planets in here. By the way, the colleague from Aries Nainital, who is visiting us, the director of the PhD studies, gave a talk in the physics department, Central Astrophysics, earlier this morning. He has done a lot of work on this solar coronal and coronal heating problem. So it turns out that this is not thermal heat because you see the surface temperature of the sun is 5,000 degrees Celsius. When you go to the corona, it's a million degrees, right? Whereas the source of energy is in the center of the sun. So typically your first law of thermodynamics tells you that what happens. So it's not thermal. It's really because of magnetic field. It's magnetic field. The magnetic energy is dissipated to create thermal energy. So wherever the magnetic field is magnetic dissipation, that lights up the plasma and the plasma emits in extreme ultraviolet and X-rays. And this is actually typically is it trace? I think it's trace. It's a trace instrument of NASA tracing satellite of NASA. It's in extreme ultraviolet image. What we're really seeing are the magnetic loops, the magnetic field lines connecting the bases of the sunspots, reaching out into the corona. And the plasma really remains frozen in the magnetic fields. And the magnetic fields which are dissipated hits at the plasma. So you can trace out the magnetic fields. And that's the sun's core. And a lot of energy from the sun's convection zone is channelized into the corona through the magnetic fields, which gives rise to a very active star. Sun's corona looks like this. I guess this is something that, again, most of you have not realized. Where does the name coronavirus come from? This is the coronavirus. The spike proteins, this is true. This is not a joke. Okay, this is true. The spike proteins of the coronavirus, the SARS-CoV-2 molecule, actually looks like these extended structures in the sun's corona. And that's where the name coronavirus actually comes from. This is the truth. Okay. Corona means a crown in Latin. Essentially, the spike proteins look like a crown of the coronavirus. So essentially, that's the analogy that we make. So this is the physical connection to the coronavirus. Although that's the connection ends, we solar physics have nothing to do with coronavirus. Okay, the corona is a fantastic dynamical place. Okay, what you see here is not a simulation. It's not something we have made up. It's an actual observation of what is known as a magnetic storm, solar magnetic storm, a coronal mass ejection, which is escaping from the sun. These are usually associated with solar flares, which are again magnetic storms. They release on the order of like a few hundred million uh, atomic bomb equivalent of energy at the same point in time. Um, what you see is a cartoon, that's a cartoon of the Earth for scale, to tell you what is the typical scale of the universe. Just for comparison. Right? Of course, thankfully, we are far away from the sun's curve. So by the time these storms come and hit any planet, they are reduced in intensity. But still, there are serious impacts when I talk about some of these impacts, which does impact our technologies. Um, this storm we got the Diwali storm because we predicted. We were the first ones to actually predict that there will be a storm which will hit Earth during the Diwali time. Our group at SSC and we got the Diwali storm, and it was actually in the news because of successful prediction. What we see now is a similar storm that we saw close up now. Again, this is observed through the last photograph on the European European Space Agency's solar spacecraft. The inner part of the sun is blocked out to the spacecraft because otherwise it saturates the detector. There is so much photons from the disk. Then you can see the faint storms that are propagating away from the sun, and you see them traveling in interstellar space. Sometimes these storms can come and hit. They're not always our direct hit, but sometimes they are. There is also a continuous flow of winds, plasma winds, which is of supersonic speed from the sun, which flows out and defies the heliosphere. That's the background environment of all planets. That's always there. The storms are water-based. Just like you have the normal weather, atmosphere, and then you have hurricanes and cyclones. The magnetic storms are water-based in space, which we call space storms. One of the most beautiful effects of that is aurores. So essentially, the energized solar wind, which travels and hits Earth on the order at speeds on the order of 250 kilometers per second, the solar storms can travel at the speeds of, on the average, about 750 kilometers per second. Um, they come and energize atoms in the upper atmosphere of Earth, and they come back to the ground state. They radiate photons, and depending on which species has been excited, we see different colors, and they light up the northern skies as well as the southern skies beautifully. They don't, you don't see auroras at low latitudes because the Earth's magnetic dipole moment, the dipole field configuration, is such that the Earth's magnetic field lines are open near the North Pole and the South Pole. The solar wind and the solar storm plasma can come through this open magnetic field lines and reach lower altitudes of the atmosphere where they can energize the atoms. Whereas in the equator, the Earth's magnetic field lines are closed. And the closed field lines essentially trap the solar wind and the solar storm and doesn't allow them to get through to lower altitudes. So you don't see the auroras at, for example, places like India, but you see them at very high altitudes. When you have solar storms, they also impact because they carry vast amounts of magnetized charged particles at high speeds. They can impact satellite operations. They are hazardous to sensitive electronics on satellites. There are also doses of high cosmic radiation, and typically they are accompanied by extreme ultraviolet and X-ray flux, which is bad for human health, astronaut health. So space weather, as it is known, and predicting space weather is now become a very important field in the modern space era because we all come to know now in the past few decades that we need to protect our space technologies and astronauts in space from this changing space environment, which we did not know 50 years back that it exists. We only know in the last 50 years that the environment outside of Earth and all planets is extremely dynamic because we see now through Earth, thankfully, because the Earth's magnetosphere, the Earth's atmosphere protects us from the solar wind plasma and the solar storms, as well as the extreme ultraviolet and X-ray flux, which is important. What you see on the left is the opening up of flight traffic over polar routes, and this has happened because of the availability of space weather predictions. So, for example, if you want to fly from New York to New Delhi, the shortest distance is over the poles, a great circle. On a sphere, 2 points are connected by a great circle, that's the shortest distance. So, to conserve fuel, you like to fly over the poles. But the polar regions, I just explained, are the most susceptible to storms from space and space weather. So already the flights were limited, but now, given that we have at least reasonable amount of space weather forecasting capabilities available, we can plan flights over the polar routes, and this often happens because this is something that can conserve fuel. And if you have predictions available, this is useful because the sensitive sensors, altitude sensors, speed sensors, high frequency communication between the pilots and the ground stations are all impacted by space weather and the varying conditions in space. Your stuff that you take for granted. For example, mobile communication, GPS transmission networks, satellite TV broadcast today, which all of us use, are subject to a slew of satellites which are distributed in space, and all of that is actually susceptible to space weather. And therefore, although you don't realize it, space weather impacts almost everyone. And we just in do see satellite outages. We have heard that in the month of February, out of about 50 satellites were launched by Starlink, 40 were lost due to a space weather. Okay, so that's about space weather. Changing technology to space. Let me now come to something that is a little closer to our hearts and probably also yours. Um, you've all heard about climate change, global warming in the recent times. We also realize that all planetary climate systems are driven by the solar radiation. Right? The natural driver, I'm using the word natural here, so let's be careful with it, of all climate systems is the main source of thermal radiative energy, which is the sun. Not just for the Earth, for all climate systems, right? Okay. Now, the sun is a cycle, which is known as sunspot cycle, which is the famous 11-year cycle of sunspots. It turns out that there are variations in the amplitude of that sunspot cycle. You see there on the left hand side plot, on the y-axis the number of sunspots, on the x-axis is time, and you see the amplitude of the cycle varies by quite a bit. And between 1645 and 1715 AD, the sunspot cycle disappeared. So there were no sunspots observed in the solar surface. That period, which is pretty intriguing, we're still trying to figure that out, is known as the Wandering Moon. It turns out that the severest part of the Little Ice Age also coincided with the Wandering Moon. And you see a painting by Henrik Averka, a Dutch painter, of a river near Amsterdam, which is completely frozen. And this painting is from the Little Ice Age. And we know that typically rivers in Netherlands or even England doesn't freeze in the winters. Okay? But it did during the Little Ice Age, when at least in Europe, was a sort of global cooling was documented. So this particular link, in fact, has been widely cited as something that motivated further look into the sun-climate relationship. This has also been widely abused by people, particularly climate skeptics. Um, so it turns out that the sun's radiation energy output, which was unfortunately known as the solar constant, I think the astronomers have been blamed for that, because we named it the solar constant, is not a constant. So you see here on the top right hand side, the blue dot is what is known as the total solar radiance, the amount of energy from the sun uh, per unit area, per unit time, arriving just outside of Earth, so at Earth orbit. And you see that that's real. That's not a constant. Now look at the lower plot there. That's the sunspot cycle. There's a number of sunspots versus time. Okay. Now, that variability is actually very small in the total solar radiance over typical decadal time scales. So small, in fact, that we will send satellites up to be able to measure the small differences, the variations in the total solar radiance. Okay. And that happened in 1978. The first radiometers were sent out into space, where it gets precise determination of the solar radiation output, and it's perfectly coupled to the sunspot time series. So that's not a surprise. Now you look to the left there. That's now actual observation. Now remember, none of these observations existed before the space age. So was launched in 1996. So we're talking of the last 2-3 decades, okay, of observations. You see those, you see the sun rotating. The sun rotates. So there's multiple images of the sun taken over months. You put together to make a image, and that's an actual observation. You see the sun rotating. So whenever you see the sunspots, you see that the corona of the sun is also extremely bright. So when you have sunspots on the solar surface, then eventually there is more energy enhancement from the sun. in all wavelengths, starting from X-rays, ultraviolet, to in fact the visible also, such that the total energy output increases when there are more number of suns. The reason is essentially the magnetic field acts as a perturbation on top of the thermal heat transport, and it adds on to the normal thermal radiative heat transport of the sun, such that the total radiation output is actually coupled to its magnetic output. Now, this then raises question that when the sunspot cycle varies, the magnetic activity varies. This also ends up varying the total radiative output. Then could that not impact galactic values? So, of course, it could because it's a natural driver. The question is that the most important driver of variability? If you calculate the base temperature, like a zero climate model based only on radiative balance, you come pretty close to the Earth's temperature, except that it will be off by some tens of degrees because of global, because of essentially you miss the greenhouse effect. If you add the greenhouse effect, it adds up. But then we see variability beyond that in the last 100 years. I want to talk a little bit about this. Okay. One thing that is important to know is in half an hour, the sun provides enough energy output to sustain human needs, all needs of humanity for the whole day. So there's a way to harness that energy, the cleanest and the best form of energy to drive our needs. But this is something, of course, that's not possible because we still don't have very efficient sources. So let me get at the climate so. So we see this link, but then direct observations of sunspots only exist from only 1611, 400 years, right? Now, climate history to reconstruct and figure out what has happened in the past to be able to look at correlations and connections. 400 years is not enough. You need to really have much more long-term observations. How do you figure that out? What has happened in the past and what's sort of the meaning of that or the connection between solar activity and that? Well, to do that, there is this very beautiful sort of method which I'm not an expert on, but when I was in Montana, I had a colleague in the Earth Science department called John Fisk. I don't know whether you've heard of. He has some lakes named after him in Antarctica. He used to go to Antarctica to dig out ice cubes, ice cylinders, ice cores, and also collect bacteria from the lake beds of the primordial lakes in Antarctica to look at the origin of primordial lakes. Anyway, so I have friends who used to do this, and this is a fantastic field and very intriguing. So I'll tell you a little bit of a story here. So the sun's magnetic field that are produced into the sun come out into the sun's corona, and through the solar wind, they get distributed across the solar system. Now you have this very energetic particles called cosmic rays. They originate outside the solar system, the extragalactic origin, in various processes. Supernova is one of them. But if you look at them, their flux is pretty much isotropic. They seem to be coming from everywhere in the universe. The low energy part of the cosmic rays are actually modulated by the solar activity. These are charged particles, and magnetic fields of the sun can trap charged particles. So the sun's magnetic activity is stronger. It acts as a stronger filter for the cosmic rays, and lower amount of cosmic rays reach power. And when the sun's activity is weaker, they cannot filter out the cosmic rays, and more cosmic rays reach. And the cosmic rays, when they hit the Earth's upper atmosphere, they go through a set of reactions called spallation reactions. And they produce multiple nuclear reactions all the way from the upper atmosphere to the ground level. One of the byproducts of this is the cosmogenic isotope beryllium-10, which is a half-life of 1.5 million, which is pretty long. And so you produce this beryllium-10 isotope in the atmosphere. Snowflakes which form in the atmosphere absorb this beryllium-10 isotope and it snows and it collects in the ground. And if you go to a pristine area which has not been contaminated by any human activity or not been mixed in any other way, you are collecting pristine samples of ice which has the history of beryllium-10 isotope from the past. And because it's a long 1.5 million year half-life, you can explore up to something like 10 thousands of years of past activity. So what they do is they go to Antarctica or they go to Greenland and they dig for ice. And the deeper you are into the ice, you are sampling very old snowfall. And take this cube and transport them back. I think in Goa, we have this facility in NCOR. They have a ice storage facility. The best ones are in Boulder, at Nankar Boulder. Um, Now you actually take out the shapes of the ice and you can do ice, basically put them under spectroscopic analysis to figure out the abundance of derivative at different depths in the ice core. And remember the different depths of different times in the past. From that, you can invert solar activity. It's all right. And in this way, this is this beautiful process of I mean, I find this completely amazing. There's so much physics and science involved, starting from astrophysics to all the way to geophysics here. And you eventually get the past history of magnetic activity of the sun. You can do the same thing from carbon 14 um, uh, isotope in 3 weeks and get back the sun's past magnetic activity. You can use the oxygen 18 isotope to recover the global temperature because the formation of that depends on the global temperature. So you have these various means of doing what is called paleoclimatology. And also, to some extent, we don't have an equivalent name for paleo-solar, whatever that's that. In principle, you can actually figure out the past history of the sun cycle. And you can put it together, and people have done that. This is from Elias et al. Physical engineers a long back. But they showed that in the past, in fact, there seems to be a very good correspondence between solar activity and global temperature element. So departures to the average temperature and the sunspot rate. And the problem was that if you look at the last, you know, 100 years, solar activity also increased rapidly. So did the, the climate rate, right? And this is where the story diverges between climate modelers and physicists and people who come in with a blind faith to do science, right? And this is also a story of correlation is not causation, right? This is why when we are still in business and physicists are still in business and climate models are still in business, right? If you look at it naively, and climate skeptics who try to sell this story, you look at it very naively and say, oh, look at this. We are fine. It's just the sun, right? Okay, it is not just the sun. And this is something that has now been worked out by climate modelers. And what you see here is simulations from the IPCC public. On the left hand side, what you see is two simulations. Y-axis is again the temperature element. The x-axis is time. The blue simulation is thick because the thickness is the uncertainty range in the climate model simulations. The blue simulation is with climate models, global circulation models using only natural forces. The natural forcing you mean the solar radiative forces, the changes in the solar radiation output and the volcanic due to volcanic emissions. The simulation data plotted in pink is the one that uses natural forcing plus the forcing due to anthropogenic causes, which is because of greenhouse gases, right? And the blue curve, the black curve, is actually observed here. And this beautifully drives home the point that the sun is not responsible for the global climate change that we see in the last 100 years, but that you have to include anthropogenic forcing or greenhouse gas, the equivalent forcing to greenhouse gases in the simulations. We will to reproduce the observed change in the global climate, global temperature record, which can tell you that it's really due to man-made or anthropogenic causes, right? That in the last, at least in the last 100 years or so. And the reason that you see is actually here on the right hand side. Look at the concentration of greenhouse gases, carbon dioxide, methane, nitrous oxide. They have rapidly increased in the industrial era, giving rise to this rapid climate change. And the Nobel Prize in Physics in 2021 actually didn't go to physicists to some extent. It went to climate modelers. But again, as I said, that when you grow old, you stop distinguishing between various fields. I have serious competition now with Bhakra Awards. I don't know, I think I can't compete with that, but uh, this is nice. Right, but anyway, so this is something that is due recognition. Because they were one of the first ones to actually point out the role of both carbon dioxide, pointing out carbon dioxide levels rising very rapidly, and climate models also uh, played very important roles in putting this inputs into climate models. Develop the first comprehensive picture of how global warming is being driven primarily by artificial causes. Okay, so with that, sort of two different stories of space weather and our climate system. Let me talk a little bit about how we explore the sun. So the way we explore the sun is we build models, we use observations, um, and we can do theory, right? So what you see here is a simulation of the generation of magnetic fields inside the sun. Again, I'm not going to go into technical details. This deals with the dynamics of magnetized plasmas, the subject known as magnetohydrodynamics. If you have three dynamics, where you typically deal with the Navier-Stokes equation and the heat equation and the conflict equation. In magnetohydrodynamics, you deal with all those equations. You also deal with the magnetic induction equation, which follows from Maxwell's equations and yeah, Lorentz equation. And also much more complex deal with multiple different scale heights in pressure and density that you observe in some transformation. So, but now we have the power with computational models and the theoretical understanding to be able to understand what produces the magnetic fields inside the sun, and in fact push that understanding to make predictions of how the sun's activity will look like in the future. So what you see here is a result of one of our predictions that we had in 3 years back. The red curve is a simulation, the black curve is actually observed sunspot time series. So you see that we have been able to reconstruct. This is the first model in which we reconstructed century scale sunspot observations and also made a prediction through one single continuous run of the sunspot cycle. So we predict that the next sunspot cycle, which is going to peak around 2025, and last until 2030, is going to be similar or just slightly stronger than the previous sunspot cycle, which implies the radiative forcing of the Earth from the Sun and the space environmental conditions are going to be similar to what we saw in the last 10 years. This was very different from many of the other predictions that happened before this, because you see, there was this rapid increase in the transport cycle activity. Then again, there was a rapid decrease. And people who do pseudoscience and only look at this correlations without really understanding the physics of it would look at this and extend it. And many people did that and actually got a published paper saying that there is going to be minimizing activity because the transport cycle has been falling for the last 3 cycles continuously, and you will see a very weak or no cycle. But we were one of the first to actually predict that the transport cycle could even be stronger than the previous cycle, but it's going to be still. So we can push this computational understanding, the theoretical understanding and computational models now to predict the space environment in terms of long-term decadal scale, which also acts as inputs to climate models. We are also now, for the first time in India, doing space weather forecasting. We issue weekly forecasts. So if you go to sesi.in/space weather, you will find our space weather forecast where we predict the possibility of solar magnetic storms, and we also assess the current space environmental conditions in terms of plasma winds and magnetic fields near Earth, and we issue alerts in our web pages. We also have a Twitter handle and Facebook handle through which we issue these alerts for last one. Let me finally come to the sun and the sustenance of life in planets, and what this understanding implies for uh, exploring exoplanetary physics or searching for habitable lives beyond our own. And this is where I think something that will excite a lot of you as well, because this has to do eventually with the interaction between sun and planets, which which many of you are also interested in terms of more on the planet itself. Okay, so we have sort of seen examples of, in fact, evidence, real observations, the sun's activity varies. So all stars' activity varies. There are magnetic storms, there are radiation changes in its radiation output. So the sun or stars is the most dynamically important object that forces any planetary system. Right? Now, the atmosphere of planets is the most susceptible to this, not the surface or the nucleus. The atmosphere, remember, stops most of this activity from reaching us, and that is why we are alive, right? Which also means the atmosphere has to bear the brunt of all these activities because it's stopping it. That there are some impacts that happens. These impacts include heating of the atmosphere and energization, which means that if they energize enough, they'll expand up and they will be caught up in this plasma flow, superstellar plasma flow to the sun, and they can escape the Earth's ground. So there will be atmospheric escape possible. Um, uh, if in fact there are no magnetic fields in planets, you lose much more atmosphere. And I will try to give you this, prove this to you by citing two different examples, one of Earth and the other of Mars. So here is a simulation that we performed of interactions between magnetized fields from the sun and the dipole magnetic field of the Earth. And again, we're the only group in the country who are capable of doing such simulations. When I came back in India, I had expertise on dynamo theory, but I had no expertise in such things. And I realized that for India to develop in the domain of space weather sciences, to be able to protect our space-based technologies, we need to be able to develop the computational capability to do the simulations, which were always being done by NASA scientists. We were nowhere in the field, right? So this is efforts over past 5 to 10 years to multiple students, and eventually we are here where we can do it as good as anybody else in the world. So what you see initially in the simulation is the Earth with the dipolar field configuration, then the supersonic winds the sun, which is imposed as a boundary condition on the left, comes and impacts the Earth's magnetosphere. You see this formation of the long magnetic tail on this side. The most important dynamic sphere really is this part. You see the Earth's magnetic field gets squeezed and squeezed and squeezed here, and eventually forms a bow shock. A bow shock is a region, a shock of sharp contrasting density, where there is a massive increase in density on one side, where the magnetic fields also are very compressed, and that adds up. So the extreme high density and pressure, associated pressure, can stop the solar wind in its track. So is that, and remember that side is the day side, which is facing the sun. So the onslaught of the solar wind never stops. The bow shock region, which literally stops the sun's activity, the solar wind and the solar storms, from penetrating further into the Earth's magnetosphere. So if the Earth's magnetosphere was not there, the situation would have been very different. And the atmosphere is actually very thin compared to the magnetosphere, which extends up to hundreds of thousands of kilometers. Right? The atmosphere is much medium. So the atmosphere is cocooned and protected by the Earth's magnetosphere from the solar wind. Right? Okay, so that's Earth. And here is a parameter space study. We like to see, that's a beautiful simulation, but we like to do the physics of it and understand what happens. So this is Earth, and this is the location of the bow shock. This is in terms of the radius of the Earth. And this different simulations for different speeds for the solar wind. So this is the lowest solar wind speed, which is like about, I think, 300 kilometers per second, and this is when you make it all the way up to 8 times is this one. So 8 times the observed solar wind speed. So when you have faster solar winds, the bow shock starts forming closer and closer to the Earth. Which means that if your activity of a star is very strong, the magnetopause or the bow shock, which stops the solar wind, will start reaching closer and closer to the Earth. And eventually, if you have a very active star, then that will penetrate into the atmosphere of the planet and will start taking the atmosphere, right? The sun and the Earth's magnetic field, the sun's magnetic field, and the speed of the solar wind is just perfect so that the solar wind does not reach the Earth's atmosphere. This is something that is fundamental not just in the solar system but any planetary system for the production of atmospheres. Mars is a nice case study. So at about 1.5 billion years age, Mars was known to have a liquid iron nickel core, which had vigorous convection and fluid motions. And it was believed that at about 1.5 billion years, there was dynamo action inside the Mars interior because of the existence of the liquid iron nickel core. So it had a strong magnetosphere, which was strong enough to protect the Martian atmosphere from the onslaught of the solar wind. And at that point in time, it is believed that Mars had a thick enough atmosphere, uh, which also had water vapor, and it had sustained greenhouse gases. So it was a warm Mars atmosphere, which could have been conducive for life. And it is this thinking which drives so many missions to Mars to look for signatures of what survives. Something happened. We don't quite know what happened between that time and this time, which resulted in the so this is the current age of Mars, 4.5 billion years, where now we observe the Mars planetary core to be dynamically quiescent. It's no longer a liquid core which is rotating. There is no conversion in it. And we also know from satellites we have sent and which have measured the magnetic fields around Mars that it doesn't have a global magnetic field like Earth. It has this localized mini magnetospheres, small cluster magnetic fields, but there is no global magnetic field. And unlike Earth, unless you have a global magnetic field, you can't stop the solar. And we also now see that Mars has a very cool, very thin carbon dioxide rich atmosphere, which is I think on the order of 100 meters. 100 meters, not even kilometers. So it is not believed to be suitable for life at least at the surface level. So now you start digging, right, to see if there can be life below the surface. So what happened to Mars? So we also simulated Mars. This was last year. Results were published last year Mars simulations. Okay, so what you see is very intriguing for Mars. So what you see here, is a red planet, which is Mars. Doesn't have any global magnetic fields, and just like the Sun, like the Earth's simulation, we simulate this with a box containing planet Mars, but now without any dipole field, and we let the solar wind. What happens first is that this plasma from the Sun and the magnetic fields from the Sun comes around and drifts around Mars, creating what is known as an imposed magnetosphere. It's not a natural magnetosphere. This imposed magnetosphere and these white field lines, these are not of Martian origin. They're actually solar magnetic field, sun's magnetic field, which has been carried by the sun's winds, the plasma, and have drift around Mars. But unlike Earth, where the magnetic fields are fixed and remain and stop the solar wind, these fields are continuously skipping past with the solar wind around Mars. So it's a dynamic imposed atmosphere, not a static one. So essentially, as the solar wind flows, this magnetic fields and the plasma skips past the Martian atmosphere continuously, and it's coupled to the Martian atmosphere. And because of this viscous coupling, it continuously erodes the Martian atmosphere. And you let this process run for a few, millions of years or billions of years. This will eventually result in complete loss of atmosphere. So Mars is a beautiful case study of what will happen if Earth loses its dynamic, its liquid outer core. Well, we still have a few generations because the atmosphere will not be lost immediately. It takes few millions of years for the atmosphere to be lost. But eventually the Earth's atmosphere will be lost if there was no geodynamo present inside the Earth's core. And this is another beautiful example of how physical processes transpire in the star inside the planet that we live in to make life possible. All right. So this is the global system of satellites that are in space, observed in the solar system in the last few decades, and this is primarily driven by the importance of being able to predict the space environment around Earth, because we have now realized that all our space is technology. and everything that we rely on today, including internet, mobile connectivity, GPS networks, high frequency communications, depends on space weather. And to characterize the solar activity and the space environment, we have something like 30 satellites on there. We are late as usual. Also because the community is very small, and in India we have always ignored engineers. That's a serious problem. We've always overvalued pen and paper people who can build this. So we don't have many people who can build instruments and machines. But that's a big lacuna that we have in the Indian system, because you realize that at the end of the day people count applications for informations, right? They don't count what contributions you have made in setting up a laboratory or teaching program or building an instrument. Happens everywhere, right? Even in our institute. Anyway, so we are finally building our first solar observatory known as the Aditya L1 satellite, which is going to be hopefully launched. I'm not going to put a date on this. We hope within the next 1 year. This is going to be a comprehensive solar observatory. In fact, Deepankar here has been involved with this mission in leadership role for a long time now. Was one of the early pushers of this mission, was also part of the science working group. Um, this mission is going to look at the genesis of solar magnetic storms, uh, the diagrams the sun's outer axis, the sun's corona. It's also going to look at how fast the storms travels from the sun in order to predict the arrival times. It also has instruments to measure the local institute just outside of the plasma conditions, so that we can understand how the space environment is changing, and figure out its impact on our space-based technologies. And multiple missions and institutes are involved in this mission. There's 7 payloads. I'm not going to go into the technical details of it. But when it's launched, it's going to be one flagship mission on par with some of the best missions, solar missions in the world. I'm coming to the end of my talk. Finally, in about 4 billion years, the fuel, the nuclear fuel, the hydrogen that we so love, uh, you don't feel, but we should, inside the sun, is going to come to an end. When that happens, the typical nuclear reaction is converting hydrogen to helium. Um, that reaction is going to stop. So suddenly you have a loss of that balance I started talking with, between pressure and gravity. And so there's going to be a collapse of the interior part of the sun. And that collapse, the gravitational collapse, is going to release gravitational energy that's going to heat up the outer parts of the sun, igniting helium fusion in the outer shells, which will heat up the outer shell even further, resulting in the outer part of the sun expanding rapidly. That rapid expansion will create a star in its evolutionary phase known as the red giant. The sun will eventually become a red giant, and it will eat up all the inner planets, including. So, if you have still managed to survive until then, 4 billion years down the line, we have not killed each other somehow. The solar system is no longer going to be harmed. That's for sure. So unless we find a new place, we are all going to go extinct. This is what will remain, because you see, if you train your telescopes to other parts of the universe, cosmos, where stars like the sun have died, what is be left behind for the sun is a white dot. You see that little tiny dot, it's like a diamond in the sky, it's really very cloud. So the helium fusion eventually stops. You have full of carbon, and there is no more reaction spot possible to fuse carbon. Temperatures are not high enough, so it's a dead star. It's a small, little, compact, collapsed object with about half the mass of the sun, but the size is like typically of the top, typically like the outside. So it's like very, very dense, compact star, which is held together by electron degeneration. That's in the middle. The outer part is this blown away part of the solar system that glows beautifully in the light of the dying star, which is the white dwarf in the center. Eventually, all will go black and dark because the white dwarf will cool off. This is known as a planetary nebula. the end of a stellar system. I've forgotten what this is. Is this the ring nebula? I'm not sure. It is the ring nebula? Yes. This astronauts are very in your universe. The ring. So this is the ring nebula, and this is how our solar system will get in about 4 to 5 billion years down the line. Beautiful. But also means that if we have not found another place in the universe by then our progenitors are going to end. I mean, geologists saying that we think about such large time scales, unlike the physicists. But look at astrophysics now, right? I mean, right. So what happens to life as we know it? And so I'll leave with that question because I mean now we are ending science and nearing the beginning of philosophy, right? But I'll leave you with this. I don't know how many of you recognize this. Star Wars 4, A New Hope, right? This is Luke Skywalker in his home planet Tatooine, somewhere far away in the cosmos, looking at double sunset. Let me remind you, if you have not read it, such a system has been discovered, where there is a planet orbiting a binary star system, right? So perhaps our hope is to find a habitable planet way beyond the solar system, right? So we always think that we waste a lot of money on the stupid astrophysicists, just a source of waste of money for human beings. Because we send this telescopes are $10 billion JWS, so unbelievable, right? Such a waste of money, don't you think? We are sending these rockets up. Completely useless. Who wants to study Mars, right? There's so many problems of it, right? But think of it. In 50 years, we have not even managed to send rockets up. We have not even managed to establish a colony on Moon. And we're thinking of leaving the solar system and finding another habitable planet. It will take you billions of years to get there. So if you don't begin now in investing in technology and the thinking of it, we may end here with the end of the sun, right? Okay. So I will end there. I will leave you with this. I'm not going to read them out. You can read for yourself. I think that I hope that I've been able to live with the idea that we don't live in isolation. That our lives are very intricately entwined with the fate of our star, the sun. And in fact, the death of stars very far away, which has filled our lives, right? But eventually, our fate in time scales which are unbelievable even for geologists, billions of years, our fate will again be tied to the death of our star. And it is important for us to find out these interrelationships now so that over billions and billions of years we can invest and find out a way to hopefully sustain humanity's descendants in the cosmos. All right, thank you very much.
Thank you, sir. Thank you, sir, for inviting us. Thank you, sir, for this wonderful session. Now I will request if you have any questions, please raise your hand. Anyone else? Please.
One question, like, is it possible to have nucleosynthesis during process? Because they have nucleus gravitational field inside. So is it possible to work on
Yeah, that's a intriguing question. So so let me off. Can you hear me? Yeah. So normally we believe not. Okay. So I repeat the question. So what the question that you are asking is this: that is it possible to have nucleosynthesis inside pulsars? Now pulsars are basically neutron stars. which are emitting pulses. For all practical purposes, we call it neutral stars. Neutral stars are the dead stars which are formed from the death of much more massive stars than the sun. Just like white dwarfs, which is the death of the sun, we ending up in a white dwarf that is held together by electron signature. Neutron stars, because they are more massive, they cannot be held together by electron signature. They are held together by neutron signature. So, neutron signature pressure implies that you have filled up all the states that's available for neutrons to fill up, and the exclusion principles comes into play. And you can't really have, typically, we don't believe that you can force them together to combine and form anything else. So it's more of a static inner core, which is not dynamic. So we don't believe that nucleosynthesis is possible in the core of the neutron star. Now, neutron stars are very strong magnetic fields, and some people believe that neutron stars also have flaring activity and crustal deformations where the whole crust is explodes in this process, which is really governed by magnetic reconnection, and they can give rise to very energetic processes that can locally synthesize elements. That is possible. I think there are some examples of that in the sun's core. That kind of synthesis is possible, but not the typical nuclear reactions in the core of the sun that we know. That we don't think are possible inside of neutron stars, or for that matter, even atoms. Neutron star collisions is a fantastic source of neutrons. Gold, for example. Recently, LIGO discovered the first neutron star collision event. And there's a process known as the R process in nuclear physics. And I'm not an expert on that again, but so that process releases enormous amounts of energy that can generate high mass energy. So gold, in fact, is produced in that process.
I think that with iron, living animals like iron,
Yeah.
if they're found, we should find in it, we should find industrial elements. Do you think it's all coming from the supernova?
No, iron comes from stars, that's why it ends, right? Because iron has such a high binding energy that it can't really go beyond that. Right? So anything that goes beyond iron is supernova. Yeah. Stars can't do anything beyond that. No, they are not. They have not been. None of these elements have been. Let's be very clear. None of the elements we talked about, none of the elements we see around us, have been generated in the solar system, right? It has all come from somewhere else. That's the sun, of course, experiences, right? But not the heavy elements. The sun is not die, right? Unless the sun dies and it spews out stuff, right? We are not going to get the heavy elements. So everything else has come from outside sources. It has to.
So why is someone is not having these very intelligence in school? I mean, why it's all
It has. No, it has a view. The sun will have some. So sun, in principle, will have, a similar elemental abundance at birth as everything else in the solar system. Then it starts changing because then it ignites it. Whereas the other planetary bodies don't have nuclear, right? But at birth, you expect most of the materials to have similar elemental abundance, except what is due to a striation that's because of essentially orbiting around the spherical core. There will be some striation in elements, but still you would expect everything to have the same primordial abundance.
I was wondering, you showed the importance of sunspot cycles as well. But we have been thinking for a long time that primary or I say is dependent on number of cycles.
Yeah.
And also, as you get to utilize it, there's a strong viewpoint that was due to slowing down the progress of ocean again. You might predict that.
So middle cycles is really again astrophysical, right? In the sense that sun in the sense that sun is not varied, but the distance of solar system, the tilt of the multiple different things is because of solar radiation. Now, one has to understand that the current system is not governed by a single signal process, right? I mean, in the sense that it's not just the sun, neither is it only anthropogenic gases, but there are also natural cycles of either atmospheric circulation or even degassing. So often apparently that carbon dioxide is stored, methane is stored. Yes, exactly. That also, right? So multiple different processes can come together to determine what planet is. I mean, it certainly is not only the sun. It certainly not only the astrophysical origin. So I think all of this is at play together. Now, what I have heard that it has been told many times that in the past history of time, the global temperature has risen much beyond what it is today, and therefore we should not worry about it. And this is, I would not like to comment on that because I'm not a climate physicist. I think I'm stretching my nose out too much. But again, I have heard this being countered by climate physicists saying that the change that is happening now is too fast. In 100-year time scale, such a change has rarely happened. And given that the change is not natural and we are changing it, we may reach a tipping point from where we will not be able to come. So, given that that scientists, I can believe so,
but in the past also, when the temperature was facing that led to extinction.
right, so that will happen. So we can decide not to bother about it. We can think that, well, like some people come on COVID, like, let the weak people die. We can, we can have such a, we can have such an outlook that we don't care, right? Or we care. So I think it depends on your outlook. So yeah. But yeah, I mean, frankly, I find that from my childhood to now, I think Calcutta has suddenly become internal. Look at Bangalore, what these people like people have done to Bangalore. I mean, the story for people, right? Uh, not people, but the IT people, right? No, but it's bad planning. I mean, eventually, can't blame any particular people also. I think it's bad out of planning. You lose trees, right? It's just saying, I mean, Bangalore is such a beautiful place. I went to one place. It's lost its lakes. It's lost its, in fact, the flooding is not even of Bangalore. Right? It's just terrible.
I have one small query. That is, okay, we now understand after listening to you
Thank you very much.
that there is a good system to watch out for the possible hazards on the space for the Earth. Now,
Reasonably good system. Let me just say that we are still not very good at predicting solar flares.
taking this entire world.
No, I'm talking about the world. When I'm talking about we're not still not necessarily very good at predicting solar flares, I'm talking about the world. Nobody is. We have a very good idea of that it might happen, but when exactly it might happen. It's like earthquakes, right? You can't predict, right? So we can predict based on observed source code, we can predict that this source code is going to flare, but when we cannot say.
No, just three words identify what kind of specifically what kind of problems other than the ones we discussed, like meteorite impacts, large asteroid impacts, and all stuff. If you watch about those, then what are the practical steps being taken to counter?
So asteroid impacts, yeah. I mean, people think that dinosaur extinctions were also driven by meteorite impact. Practical steps. I don't think you can take any practical steps.
But just say, that's a sending a space to deflect that.
It's not deflect. It's going to impact the asteroid to create, get some samples and also deflect different deflection of course with momentum transfer. But if you have a big asteroid coming to you, it's a bit tough to do anything to stop it from you. So yeah, that's possible. I mean, certainly possible.
And if the Indians are attacking, that people think they want.
You can spot them. They'll be sitting next to you. Not know. Well,
Yes, I have a few questions where firstly talk about the R process and the S process. So those nuclei, when do you think you
I
are
have,
in this stage?
I have zero expertise in this. So I'm happy to completely raise my hands and say that I don't know anything about the R process and the S process except that they can operate in neutral star molecules.
Yeah,
You can talk to this guy's friend Vishnu Mukhopadhyay, who's a particle physicist in IIT Kolkata, and he'll be happy to help you with this. I'm sure that your physics department will have people who have particle physics. I don't have any experience in R process.
No, my question would be like, at which stage of the evolution of the solar system do you think those atoms have been included in the solar system?
So the R process, I mean, as per right, it happens in different star molecules. I don't even think that it happens in a typical solar system. It doesn't. To my understanding. But if you really talk to a particle physics to understand that. I think that's unique to very high, high energy cosmic levels like nucleus and so on.
And my second question would be, chemically speaking, Mercury is considered as an outlier in the solar system evolution. They usually higher concentrations of iron than the technically more refractory materials usually present in Mercury. So, physically speaking, how do we explain the evolution of Mercury in a closer proximity to the Sun than any other more refractory?
See, I give you a warning. Never ask a chemistry question to a physicist. I mean, so I have no idea. That's the truthful answer. You want a long pointy answer, I can give you. But I can tell you that I am a sort of a illegal alumni of Presidency College. I studied chemistry in Presidency College for 1 month. And left it to study physics in Vidyasagar College for 1 month. Then left Vidyasagar College for St. Louis College physics. Eventually, that's why I got my physics. That was my experience with chemistry. But anyway, yeah, sorry, I cannot answer that question because I don't know anything about the evolution of Mercury. Do you know anything about Mercury? But they are using Mercury in a liquid mirror telescope that I have in it. It's the only one in the world, 4 meter class telescope. But they are putting Mercury on a telescope and rotating the telescope fast to produce a parabolic mirror from the rotation of Mercury. Mercury has a very good reflectance. But I know the only thing I know about Mercury, as I know of all chemistry stuff, is very poisonous. Yeah. I was only talking about the edible soil. Yeah, sure. Yeah.
Well, most of them rotate in the same direction.
Right.
Like if they come in the same order,
Yeah, so that's a very good question. So normally what we expect is this. So when talked about the formation of this planetary system from a protostar. So from a protostar you form a star and other planets. And typically, angular momentum is just like linear momentum. Even angular momentum is a conserved. So what you would expect is all stars and planets to pick up this angular momentum direction, which will be picked up from the original angular momentum collapsing protostar, right? Because angular momentum has to be there. The only way you explain a rotation which is opposite to what is being observed, if there is a process which has converted the original angular momentum of the system to a different angle, which implies there has to be a torsion. So that is possible either through a collision, which had a tank collision with a planet in the opposite direction, moving with the collider system moving in the opposite direction. It can also be explained to very complicated ionic process interaction to multiple different points. So a couple of different possibilities. But otherwise, you do expect that most of the system that has been born from the rotation of protostar should have the same direction as the other.
clear surfaces, clear power flow. So, would it be the second option?
It's possible, but the point we also theoretical possibilities. What has actually happened, of course, you don't. That's the problem. But theoretically, these are possible. purely impossible. That's just not very No, it doesn't have anything to do with the direction. Xenos, in fact, is online. It doesn't have anything to do with just like Mars, it is reinforced lattice. It doesn't have and the magnetic comes from mission, honest mission, and from mission, and very much magnetic. But Venus doesn't have.
Professor Nandi, I have a small query.
Sure.
Our system, we are collecting samples from different asteroid bodies in last year. So with these evidences, how far we can go towards the big bang? So far, we know about 4.56 million is beginning of solar system. Is it possible to go beyond from these materials?
So from asteroid samples, most of the asteroids that we have here are mostly solar system asteroids. So from there you can collect samples, you can do this isotopic analysis and abundances and all that, and from that you can figure out about the origin of the solar system and perhaps also trace some elements to other parts of other systems. But with that you can't really go very far. I mean you can go up to maybe something like 10 billion years or earlier than that. If you want to really go to the Big Bang, or your only hope is to look for radiation that survives from the Big Bang, remote sensing of the electromagnetic energy spectrum, which is essentially CMBR. Um, I have it's been told that one can also look for gravitational signatures of primordial black holes and other such exotic things from the early universe. But these are all theories, and none of this has actually been yet uh, observational data. But certainly, meteorites are a very good system for looking at the original sources. What are the original constituents? Because I think they live in some parts they contain a pristine environment of living upon.
Particularly the volatiles.
Exactly. So that itself is quite something that tells you about where you came from. Right? Yeah. Anyone is not black holes. It is not clear, right? For that, you need to come to Anil Kulkarni and talk to my colleague. I'm not going to extend my notes to other fields that I don't know. So I know where to stop. So this is where I stop. I am not going to talk about stochastic gravitational wave factor. Come to your home is up to half. Yes, so fine. So okay. So we have picked up something for him to have testing me. I'm paying. Yes. I'm out of it. We are the
Sir, the solar storm which is simulation is not simulation, but actual image. With that time scale here.
So basically, after solar storms using a velocity, it takes about less than an hour. A flare can happen for even a few minutes, the origin of the flare, but the whole event can last for about an hour. But to start from the sun, arrive at Earth, and after the force space storm to do the things, actors electromagnetic radiation. Electromagnetic radiation and some very energetic particles which travel almost close to speed of light, they arrive in about 8 minutes per minute. But the actual coronal mass ejection, which are magnetized crosses like in linear, it can take anywhere between 1 day to 3 days. So there is some time in predicting the arrival of a magnetized cluster. For the X-rays and extreme ultraviolet radiation, there is not much time. It will be very close. So, I mean, your only way to be ready for it is to they can have a forecast that there is a probability of a storm, and therefore you sort of take protection and let that probability be, right? Because once it happens for the higher range radiation, you don't have much time. But for geomagnetic impacts and geomagnetic storms, something called geomagnetic storms, which is a deep in the magnetic field of the Earth, which is induced by anesthetic currents due to the impact of solar cells on Earth's atmosphere. That takes 1 day to 3 days to happen once you observe on the subcontinental line, depending on the speed, but anywhere from 1 day to 2 days. So you have some advanced line. কোন ভিডিও কথা বলছিস অনেকগুলো ভিডিও দেখেছি আচ্ছা সেটা no that is something that is I think probably few minutes people will know when this is an observer. This one, the CME, the filament eruption, I think this is less than 30 minutes. I think I know what you're talking about. No. What is the time scale of this? I think it's less than 30 minutes.
Yeah. So that eruption is pretty fast.
It's pretty fast. It's less than 30, on the order of 30 minutes or so. It is real.
There are many images which is moved into a movie.
It's very real.
Not real time.
No, that's true. It's not real time. This is totally about 30 minutes of, I think, roughly 30 minutes what it takes for a storm to come. It's pretty fast process. Well.
That means I was a voice of the because here are higher degrees and it's seconds in so when it shop started here at the sphere for fire.
Exactly. Yes. So basically, all stars which are active stars and which are weak. So most active stars will have a weak plasma wind, and the plasma wind defines the universe. Sorry, not the universe, they are astrophysics. Physical universe is almost standard astrophysics. So all stars will have astrophysics, which is the boundary between that stellar system and the outer part of the cosmos. So inside it, everything is governed by the star. So inside the astrosphere, the star is the boss. It influences the space environment. Outside, you get the interstellar.
Sir, solar system records.
Solar system का realistic का तत्व है वो. This is a tiny part of the realistic. Physics will be universal. तो वार्महोल पे ये बता रहा हूँ इस पर तो ये वार्महोल होता है Physics दो तीन लेकर ऐसे विश्व पे था ये साइंस फिक्शन कोल्ड दृष्टि है वार्महोल में हम लोग फिजिक्स विशेष करना साइंस फिक्शन में पार्टी नहीं पर पार्टी नहीं पर we are wrong. Our science should be wrong, we'll discuss something new, but typically what works, what we know to be working in the solar system, the fields should not change as we go out. Because you're not necessarily encountering anything different in terms of materials. So it's the same plasma material, same gaseous systems that we see here.
If you let's say multiverse, the same physics will be actually
Adopt the boundary of all parts. I mean, it's simple things. I am multiversal. Like our guru is also our other content. I mean, put it the observational given science school. Hey, bhai, you don't proof. I don't want this thing. Sure.
On the figure you have to project research. There were some classes to hold that.
News, hot news, yes. So in fact, if transport to from the never from the jet. So what is interesting is So what is interesting is you see that you see the convective cells here, right? Outside the substance, but you don't see them here. So what has happened is that the magnetic field lines which are emerged from the bottom. So magnetic field lines get stretched power, they have tension. They don't like to be stretched. You have to do work to stretch. So it inhibits the convection. Because a transcriptional mode the convection part. It's basically like a fibril like stretch loading pressure coming out of the sun, the magnetic fields. And there are transcriptions around it. Okay, it moves around the sides of this magnetic flux which is coming out of the sun. And convection happens around it, not inside the substrate. Now, around here there are fluids which are they're called inverted fluids. Those kind of fluids exist uh, in the boundaries of something. In fact, that was discovered in Kodaikan Solar Observatory. Famous talk about the worship of the ground in Madras. This is very called Madras Observatory. Because special university for it. That was that university was that other people started discussing. So then called the Madras. Yes, because Madras Street also, you always have close and the outer in that case. So last one was rocks. Just like any other we don't know. We don't buy anti-sunspots, but there is something because sunspots are so strong that they change the color. They can't really change the signal. But the sunspot usually after some time you will be at the and it becomes smaller when like passes. And then they can be subtracted from the that's called magnetic pumping that happens. Time scale takes almost a couple of 1 month to more than that. Takes a a large size sunspot it will take 2 months to build up. A small size it will build up in half days. After vinegar it will start subtracting and the convection subtracting. Sorry? Does that create any special phenomenon? That's called magnetic pumping. That phenomenon. That is actually important for the diagram of process. In a very technical way, we know why it's important, but it's actually very important. Because the magnetic cycling really arises from a recycling of different components of the magnetic field between the colors higher layers and the lower layer technology. So anything that transports flux, magnetic is very important for the diagram. And this is this pumping or subtraction is a transport transfer. That is the business and assessment in the landscape. Any kind of transport in that transformation that is
Thank you, sir, for answering the questions. And that's really amazing to have you on this occasion. Now I will request Oshabi to present a vote of thanks.
I deem it a great honor and privilege to propose the vote of thanks on behalf of the Geological Institute on this special occasion. A special thanks to our guest of honor, Professor Dipendu Londi sir, for accepting our invitation and for being with us today. Your thoughts have truly inspired us, sir. I would like to thank all the audiences present here, professors, ex-faculty members, alumni, and lastly, all the students and the members of the Geological Institute for cooperating with us and making this 99th AGM a resounding success. Thank you. We have arranged some refreshments outside the hall. Thank you.